All right, we're recording. We got one final lesson in our functions unit. What did we start with? It's been a long road.
It wasn't factoring. That was the very, very beginning.
That was very,
What
very.
did we do? Let's look through my notes. Was it lines?
No, I think. Yeah, maybe. It
No, it was bubble diagrams.
was what is a function, right? And then we did function lines. We did like the basic like function, a linear function, and then we did all the parent functions, right? Then we transformed functions. Then what came after that? After we transformed functions. Man, it's been so long. This unit just tends to just drag on. I'm excited. Let's get into this final lesson. And maybe at the end, we can talk about how we will like culminate this unit in our final problem here. But we'll get to that. All right, so let me just title this stuff. Today is today. And the period is some natural number.
Today is the day after Ada Lovelace Day. Shout out to Ada Lovelace.
Tell me about it. Can you tell us about Ada Lovelace?
Well, a lot of students, I've actually just learned about her from students' journals. But Ada Lovelace was she was the daughter of like someone who was doing more of like poetry kinds of things, and someone else who was more focused on like science. And so I think her mom wanted her to not follow in the path of her dad and not be a poet. And then she effectively like became the first one to write what is now known as like a computer program. But this was like way before we had like computers in the sense of knowing what they are now.
Mm-hmm.
Like there's no actual pictures of her, it's just like fancy looking paintings.
And yesterday was Ada Lovelace Day?
Yesterday was Ada Lovelace Day. It's the second Tuesday in every October.
In every October. Okay, so is it her birthday? Was it like the day that she wrote her painting?
That's a good question. I really don't know.
I wonder. Huh. All right. Interesting fact to get this video going. I'm happy. So this is I don't want to say an annoying lesson, but it's going to be a very definition-heavy, wordy lesson, and it's going to really challenge our ability to understand the language of math. Because like I got two definitions here, increasing and decreasing functions, and these definitions are tremendously wordy. They are difficult to dissect. Let's do it though. Can you read this for us?
Sure. So a function is increasing on an open interval from a to b if for any x1 and x2 in the interval a to b, such that x1 is less than x2, then f of x1 is less than f of x2.
All right, so when I look at this, I think, okay, I want to claim that a function is increasing on an interval. So that's kind of the question. Hey, is this function increasing? Yes, it's increasing on this interval, a to b. Okay. But in order for it to be increasing on this interval, I need to pick two arbitrary points in that interval. Right? Arbitrary meaning no matter what 2 points you pick, if you then order them from least to greatest, then their outputs will also be from least to greatest, regardless of the 2 points. Would you say that's like a fair assessment of what increasing is?
I think that's a good way of putting it. I think it also might be helpful to just draw a little sketch.
Yeah.
So that we can see what we're talking about.
Let's hold it off and revisit these definitions. Can you read decreasing for us? We'll get a graph and we'll kind of work it out.
Sounds good. So decreasing, a function is decreasing on an open interval from a to b if for any x1 and x2 in our interval a to b such that x1 is less than x2, so that's all the same, then f of x1 is greater than f of x2. And that's the only thing that's different between those two definitions, and I guess increasing versus decreasing.
Yeah, the actual word that is being defined. So once again, we are looking, if I say when is this function decreasing? Your answer to that would be an interval, an open interval, not a closed bracket interval. And we're looking at no matter what 2 points I pick, will their outputs be larger than less large? Will the outputs be decreasing if I pick 2 arbitrary points? Let's do exactly what you said. Let's get ourselves a graph. We got x squared here. I'm just gonna go ahead and graph it real quick. Looks
like riding a bike.
Today. What was that?
Graphing x squared is like riding a bike. Like so familiar now. You can do it second nature.
And then when you're like 70 years old, you're nearing the end of your life. That's a little bit dark. And you pick up a pencil. You will remember how to graph x squared, just like a bike. No matter how long it's been, you just hop on the bike and you go.
I've definitely experienced, witnessing people who have forgotten how to ride a bike. So might not be the best analogy.
Maybe it's not the best analogy. Yeah. All right. So let's kind of intuitively answer this question. All right. There's some questions down here. We'll get to it in a second. But when do you think x squared is increasing?
X squared is increasing from 0 to infinity. And in my mind, I'm just drawing slope guy onto the graph.
Wait, what's slope guy?
Dude?
Slope dude? Did you show everyone that video?
I did not. But
I haven't not. Oh, I think in the video, I don't know what I'm gonna do, but we're gonna somehow get that video out to everyone. Slope dude. All right.
Link it in the description.
We'll link it in the description below. Don't forget to like and subscribe. Okay. So you claim that it's increasing on 0 to infinity. So the definition says, no matter what 2 points you pick in that interval, if we order them from least to greatest, then we look at their outputs. Those outputs need to be least to greatest. So let's say I'm gonna pick. So I'm gonna kind of write this out. Right? Claim 0 to infinity is well. Let me write it like this. Rewind. F of x is increasing. On the interval 0 to infinity because for any, I'm gonna put a little upside down a. That means for any x1 and x2 contained on this interval that you've just given me, if x1 is less than x2, then f of x1 is less than f of x2. All right, I just read the definition out there. We've kind of justified it, but give me 2 points on this interval. You don't order them yet. You can give it to me less, greater than less. I don't care. Give me 2 points or 2 x coordinates on this interval. We'll get an example going.
1/2 and 7.
We have 1/2 and 7. That's my x1. That's my x2. Okay. So I'm going to order these from least to greatest. 1/2 is less than 7. In order for this to be increasing, f of 1/2 needs to be less than f of 7. Is that true? I'm going to put a question mark above it. What is f of 1/2? We have the function. It's f of x is equal to x squared, right?
Yep. So f of 1/2 is 1/4. F of 7 is 49.
Sweet. And that is totally true. All right, so it worked for those two. Is there or are there two coordinates, x coordinates, that you can give me where the definition is broken, where we find a counterexample?
I don't think so, but I don't know how to justify that rigorously.
Let's not do that here. I think what we're trying to do here is just understand this definition. All right, but to the viewer, you can maybe start to think about how might you be able to show that if x1 is less than x2, then f of x1 is less than f of x2. That's an experiment to the viewer, right? But I do 100% agree that your claim is correct. 0 to infinity is an increasing interval because no matter what 2 points I pick, the outputs will be ordered from least to greatest. We are going up from left to right. With that said, what would be a decreasing interval here?
From negative infinity to 0?
And we could do the exact same thing. We could justify, we could claim that no matter what 2 points I pick, I'm going to get the definition to be met. But we're not going to do that for this one. Domain, range, let's just get them real quick.
All real numbers and non-negative reals.
So how do I want to write that? Maybe just 0 to infinity.
Yeah, but I think we need a bracket on that.
Yeah, no. There we go. There's the eraser. 0 to infinity. Do you see that I'm drawing my infinities for you?
It's lovely.
I need to be recognized. All right, cool. So let's look at the second one. We got the square root of x. The reason why those domain and range questions are there, just so that we're constantly thinking about them. What's the domain and range of x, the root x function?
0 to infinity.
0 to infinity. And range?
The
I think
same.
you answered the question. You know, one time, this is kind of an aside. One time, Mary Kate asked me, no, sorry, I asked her, I gave her a screenshot of a Star Wars movie. And I said, which Star Wars movie is this? And she goes, that's Star Wars. And I said, no, which one is it? She goes, no, it's Star Wars. And we went back and forth for like 1 minute. And then she finally said like, Star Wars is episode 4. You don't call it anything else. It's Star Wars. This is what happened here. What's the domain and range? 0 to infinity. Well, what's the range? No, you heard me the first time. Did I stutter? So you're right. You're right.
But I don't know. I think episode 4, like, I still refer to it as episode 4.
Yeah, but when someone says, I went and saw Star Wars, I think we all need to agree that that's episode 4.
I don't know. I don't know about that.
Let's proceed. All right, here is that function. 1, 2, 3, 4, 1, 2, 1, 2, 3. This is almost like riding a bike, but not really. It's like riding a unicycle.
Riding a unicycle? That sounds very difficult.
Maybe that's the hobby that I want to learn. I asked my class recently, what hobby do you wish you did, but you do not do? My answer was bagpipes, but a unicycle might also be on that list. All right, here's the function.
Unicycle was on my list in high school. It was on the list of things I wanted to do, but then, you know, I just realized how much more easy it is to ride a bike.
All right, I'm gonna write something. I want to hear your opinion here. I'm gonna claim that this is increasing. Looks increasing on the interval 0 to infinity, including 0. How do you feel about that?
Well, Mr. Kirk, according to the definition that we are using on this piece of virtual paper, we are claiming that we can have increasing or decreasing on open intervals. That's the definition that we're using. Now, it could be that there are other texts, other resources, other definitions out there where it does not necessarily need to be a closed interval or an open interval. It could be a closed interval. But my question is, if we're saying that we have an increasing interval from 0 to infinity, including 0 here, then look back over to the other side of our paper, and what do we have? We have a parabola. Could we say that we have an increasing interval, including 0, and a decreasing interval, including 0? Would that be allowed? Because then, like, what's actually happening at 0? You're sitting on 0. Are you going up or are you going down?
I think my heart and soul says that we can't decide what's happening at a single point. I think that in order to talk about whether something's increasing or decreasing, we need 2 points in question. So that's just my one reservation is if we're talking about a graph increasing, we should be talking about it in a broad sense and not having endpoints. But that's just my opinion, and maybe that's just the way I was taught. You know, what do we want to do? Do we want to allow open intervals, or do we want to sorry, closed intervals, or do we want to just go with what's on this page?
Well, since we're working on this page, I feel like we should just continue with what is on the page.
Okay. So we'll go ahead and say it's open. And I guess for this course, regardless of what other texts say and other courses in the future might say, just for this course, we're going to say that when we're talking about increasing and decreasing intervals, we're talking on open intervals. We're not concerned with what's happening at a single point. Cool.
An analogy for this might be like my Spanish 1 teacher learned Spain Spanish and did study abroad in Spain. So the Spanish that we learned in that year was Spain Spanish. And then when I got to Spanish 3, my Spanish teacher was not trained in Spain. So then we learned Latin American Spanish. And like both are correct. It's just like changing, like code switching, making sure that you're aware of what the class that you're in is looking for.
I think also being able to, being comfortable with change is an important skill to develop, right? Like you want to be able to go from teacher to teacher and be able to communicate with them effectively. And not just teacher to teacher, but friends and friends, courses and courses, topics. I think that being flexible is important, right? Let's continue. But there is one of, I'm sure, several wise words from Mrs. Contreras today. All right, decreasing intervals. Is this function here decreasing ever?
It doesn't look like it because our increasing interval is almost exactly the same as our domain. The only thing missing is our endpoint.
Yeah, so if we included endpoints, maybe we could say decreasing at 0, but that would also be kind of confusing. So I think, all right, let's move past this semantic argument, or not argument, but discussion. All right, there is your 2 definitions of increasing and decreasing. We got some more complicated definitions coming up, particularly on the next page, but nothing that we can't handle. Right? Difficult is not a problem. Those are not synonymous. Difficult is okay. Relative extrema. Some big new, like complete, like increasing, decreasing. You use those in your like normal vocabulary. Relative extrema. New words potentially for several people. Can you read these ones for us?
Sure. I'm just trying to think of when I use relative and extrema in my normal everyday. It doesn't happen. Even with all the cousins that I have, it doesn't happen. Relative extrema. A function value f of a is called a relative or local minimum of f if there exists an open interval x1 to x2 that contains a, such that x1 is less than x is less than x2 implies f of a is less than or equal to f of x.
I definitely meant it when I said this one was wordy and there's a lot to unpack. So I get my first question to you is when I say, just like the last time, when I say, hey, what's the relative extrema for this graph? What is your answer to me?
Well, I would be giving you a number, a function value. So it's important to note that we're looking for a number. And that number is like something that is less than everything else around it.
Yeah, because we're talking about minimum here. Let me leave a little arrow there. So
but it's only on a particular space. It doesn't have to be for like the entire domain. And so we have a local extrema at -2, what is that? -7. -7 is our local minimum. And local and relative, those are interchangeable. I think I haven't detected a pattern yet of how I use them, but I think I use global more than I use absolute for the next one.
Really, I think I use absolute more than global. And let's not get there. Let's not get there. We haven't read those definitions yet. But so I just want to say something. You claim that this is a relative minimum, but there's arrows over here. I've added them just to make sure everyone's clear that this graph continues. You're saying that that's a minimum, but like this graph keeps going down. How is that a minimum?
Because all that we need for our local minimum is that we can find an open interval so that we have one value that is less than everything around it. One y value that's less than all the other y values surrounding it.
So I've kind of given us on the page an open interval. I've given us -4 to 0, right? But your claim is that that is the lowest point on that interval.
-7 is the lowest value on the interval. Yeah.
Let's go back up to the definition and kind of like plug in these numbers. So a function value -7 is a relative min if there exists an open interval. What did I just say? I said -4 to 0, I believe. That contains a. So wait, what is a?
A is the x value. So
Right,
that was -2, I think. Yes.
So it contains a. It contains -2. And I'm going to go back up here and say f of -2 is equal to -7. Right? So the answer is still -7, but I'm saying up here that the thing that I'm plugging in to get it is -2. That's kind of important. It's like an existence thing. Right? If I said -35 was a minimum, but no point gets me to -35, that's kind of a problem. Right, so a function value -7 is a relative minimum of f if there exists an open interval. We have that -4 to 0. It contains the number that gets me to -7. And if I pick any point between -4 and 0, that's what this little inequality says. If I pick any point between -4 and 0, then -7 is less than or equal to that number that gets outputted. So like pick a number between -4 and 0.
-3.
-3. -3 is an output. It looks like -6.1. Let's just say that. Roughly -6.1. So if I pick -3, we're saying that x is -3 here. I get -6.1 in the definition hole. -7 is less than or equal to -6.1. Right? Is there a point that I can pick between -4 and 0 that gets me lower than -7?
It doesn't look like it.
Right, so with that said, we have found ourselves a relative minimum using a very mathematically challenging definition, I think. But it's pretty darn complete, if you ask me. Right, -7 is this is not Faraday, is a relative min. All right. Can you look at the second definition for us? A function value, etc.
Sure. So a function value f of a is called a relative or local maximum of f if there exists an open interval x1 to x2 that contains a such that x1 is less than x, which is less than x2, which implies that f of a is greater than or equal to f of x. So it looks like, again, the only things that we changed was that very last inequality.
So do you mind if I try to paraphrase this, or do you want to take a stab at it?
I think you got it.
All right, so just with what I've said before in the relative minimum definition, we're looking for a number right here. Let me change the color so it can like differentiate from what we had previously written. We're looking for a number.
Differentiate.
Yeah. We're looking for a number. We're going to call it a maximum, such that, a relative maximum, such that it is the largest number on an interval. And the way we check this is we pick an arbitrary value between our interval. And no matter what number we pick inside the interval, the number that you gave me at the beginning is going to be larger than all the other numbers. All right, so let's go down and see if we can find that. Is there a number on this graph on the left that there exists an interval around it? It's an existence question. Does there exist an interval around the number that you're giving me such that no matter what number you pick on that interval, it's going to be less than the number you gave me?
9.
9. All right, so I'm just gonna, so your claim, I'm gonna be a little bit tricky here. You're claiming 9 is a relative maximum.
Ooh, no. I'm claiming that 9 is a relative maximum when x equals 6. So the open interval that I'm looking at is somewhere in this first quadrant, this the right side of it. Yeah.
Yeah, so can you give me that interval? Because when you claim something to be a maximum, if I just say, hey, what's the max or the relative max? 9, fine answer. So maybe it was my fault for asking a vague question. But what you can do, if you want to be very clear, is when you say a maximum, a relative maximum, you can also give me that interval. So on what interval is 9 a maximum, a relative maximum?
9 is a relative max on the interval. It's like 2 to 8.
So let's do 2. So like here, 2 here. We got those 2 intervals. So we have this, I'm going to make this right interval here. Right. You give me the interval 2 to 8. You could have given me any other interval. All you're doing is trying to find an interval where 9 is the highest, and it looks like you found one. And then so if my x1 is 2 and my x8 is x2, my 2 is x1 and my 8 is x2, no matter what x value I pick between it, that's the idea of that inequality. No matter what x value you pick, when I get my output, it's going to be less than 9. You have found another extrema. Not negative, 9 is a relative max. And we don't always write the whole word maximum, but max is fine. Right? It is important that you qualify max and min with relative or local, because we do have 2 other words that we want to look at in a second. But yeah, there's our relative min and our relative max, and this graph has both. There's a lot going on. If you want to justify these, we'll justify those in a little bit. Let's look at these last 2 definitions to call today on these new definitions.
So we have absolute extrema. Suppose f is a function with domain D. So now we're just saying this is the domain. F of c is an absolute or global minimum if f of c is less than or equal to f of x for all x in D.
So let's go down real quick. Earlier we said 9 was a, we said -7 was a relative min. Right? Is it an absolute min? Is it a global min?
No.
And why or why not?
We have that arrow going down on the right side. We have an arrow that's going down. So that means that, well, our domain, I think maybe we should talk about what our domain is.
Yeah.
Our domain is all the real numbers. And our range seems to also be all real numbers. So can we find the minimum real number? Is that something that exists?
Well, I like to play a game. You pick a number, and I'm gonna try to find a number lower.
Okay. -5 billion.
-5 billion plus 1. Wait, no, -1. Darn it. No, but yeah, no matter what number you give me, I can find something lower. All right, and going back to what I said earlier, is -7 an absolute min? Absolutely not. That was a really good pun. That was unintentional. Because if I claim that -7 is an absolute min, then I need to look at the rest of the domain, and if I can find a number lower, then I've given a counterexample to it being an absolute min, and -5 billion is a counterexample. It's always fun to pick really, really massively large numbers that are almost incomprehensible. A billion, it's a massive number. That is like, if you had $1 billion, you'd have more money than you could like probably ever spend in your lifetime. All right. We got some increasing and decreasing intervals here, but we didn't say what the maximum was. Let's just say it for the record.
The f of c is an absolute or global maximum if f of c is greater than or equal to f of x for all x in D. Oh, were there math notation things that we wanted to talk about? There exists is like the backwards E.
Yeah, so So we already talked about for all a little bit. Instead of writing for all, we could have done upside down A. Can we fit there exists in here? F of C is an absolute maximum if.
In the relative or locals, those definitions we have.
Oh yeah, there exists. Right? That's the whole idea with these is you're looking for an interval for both of the relatives. Can you find an interval? Does there exist a backwards E, a backwards capital E? Does there exist an interval? So that's what we're looking for. And we'll do that in just a second. Let's get the increasing and decreasing on the left-hand side.
So we have increasing from -2 to, I think it was 6. And those are open intervals, yeah. And then we have decreasing everywhere else.
So I'll say -infinity to -2. And I'm going to put a comma, not a union, just because I'm considering these things separately now, rather than together. And then what do we want? 6 to infinity. Cool. Okay. Before we continue, how are we doing on time right now?
I think we're okay. It's 11:53. You have class at what, 12:30?
I think so. Is that when lunch ends?
Let me check. From my bookmarked bell schedule, bookmark the bell schedule. It's helpful. 12:30.
Okay, cool. Let's continue. All right, so how about we leave this one for the viewer? Go with that?
Yeah, so they're going to be asked, what's the domain? What's the range? What's the increasing interval, decreasing interval, and extrema?
And then the extrema. And this one?
You have a question, though.
Yeah.
For that constant part, you know that little piece at the end where you're going from, what, 5 to... Would you say that that is any sort of local or global anything?
So let's as we said in the first page, let's revert to the definition that we've given ourselves. Right? It might change based on the text you're looking at or the teacher that you have, or etc. But let's look at the definition. And if you look at the definition, which we got a lot of annotations here, sorry if it's a little busy, we have an inequality here that includes equals. So let's go down to this and try to justify whether there is a max. So this is what I'm going to do. I'm going to claim that it looks like -7. I'm going to say f of 8 is equal to -7. I'm going to claim that that is I'm going to claim that it's a max, a relative max. Does it meet the definition? Well, does there exist an interval around it such that regardless of the point that I pick in that interval, -7 is -7 is greater than or equal to the point. The greater than or equal to, I think, is the key. Right. F of 8 is equal to -7 is a relative max because, and I'm going to take this down here. F of 8 is equal to -7 is a relative max because on the interval, let's go with -6 to 10. On the interval 6 to 10, if x is between 6 and I said 10 out loud, I wrote an 8. Let me write this 10 big enough so that it covers the 2 on the page number. Right. I'm going to go back to my beginning and read myself through. F of 8 equals -7. -7 is a relative max because on the interval 6 to 10, if I choose a number between 6 and 10, f of x is less than or equal to -7. I think according to our definition, -7 right here is a relative max and a relative min. According to our definition. And now another definition might cancel that out, but not in this case. It's definitely not an absolute max or an absolute min because I see points down here and I see points up here. Cool. So we'll leave the rest of this for the viewer. Did you want to address anything else on this page?
No, I think we're good.
Cool. Oh, wait, we never said, are there any absolute, we did say that there were no absolute maxes of molecule. Cool, let's proceed. All right, asymptotes. F has a vertical asymptote if. All right, how can we define what an asymptote is? Do we know what an asymptote is visually?
It's when we have some vertical line, and vertical lines are like when x equals something, that our function gets super duper close, but never actually reaches that number, that x value.
So we've seen this before, right? Yeah. One graph in particular we've seen this before is the 1 over x graph, right? All right, so F has a vertical asymptote at x equals, let's go ahead and say this is x equals k. If and only if F has a vertical asymptote, how can we define this thing? We're not being given a definition here. Let's make it up ourselves.
Well, we need to somehow say getting super duper close to a particular x value. So is there a math way of doing that?
There is something that will be studied in depth later. Do we want to use it?
I think so.
Yeah. So we're going to use the word limit. Can you kind of give us like a quick beginner overview of the word limit in math?
Limit is looking at the motion towards something. So limits are thinking about what happens as you are going, as your x value or your y value, whatever your input is changing towards a particular number or towards end behaviors. So towards infinity or negative infinity. What that function is doing as you're moving in your inputs.
Okay, so help me polish up what I'm about to write and make sure we got it exactly how we want. But F has a vertical asymptote at x equals k if and only if. That's what the IFF stands for. The limit as x approaches, that's not how you spell approaches k. So as we get closer and closer to this k value from the left and the right, there's an asymptote if the limit as x approaches k is, so let me say this, the limit as x approaches k of the function is infinity or negative infinity. I guess I cut it out plus or minus, but is that good? Do you like that?
I think that is good for what we're doing here.
Mm-hmm.
That we're going towards an x value, and we could go towards like positive infinity or negative infinity. They could both, from both directions, it could go in the same, like up, or they could both go down. They could go opposite. Volcano, yes.
Black hole. Ripple in space-time. This could be like, I like to call them teleporters. And so as we approach that number, we're shooting up to infinity or shooting down to negative infinity. That's what we mean by an asymptote. All right, there's a math way we can write this. I'm going to go ahead and write it. The limit, LIM, as x approaches k of f of x equals plus or minus infinity. Now this little box right here, it says the exact same thing as what we just written in words. So our definition of an asymptote, a vertical asymptote, is as I approach a horizontal number, my vertical number, my output, my range, shoots up to negative infinity or positive infinity. And it doesn't have to happen on both sides.
There are some nuances I think that we are missing a little bit in this, because we don't really want to get too deep into the weeds of like one-sided limits. So like don't totally lock this into your brain right now, but just think as we're approaching some x value, we're getting totally different, like we're getting infinities or negative infinities or opposite infinities.
I guess we could do this. The limit as it approaches k from both sides, or the exact same thing. Approaching it from the left side, the negative side. Maybe I'm not going to write the negative symbol. That's kind of confusing at this moment. The left side is equal to plus or minus infinity. Or I could write the same thing with right. I'm not going to write it a second time. I probably should, actually. Just so it's complete. Yeah, I'm not going to run out of room. Maybe. Because it could be happening on just one side, like I've drawn over here now. Like, look, I have a point on the asymptote. I think that's a common misconception that there can't, like, lines can't cross asymptotes, or functions can't cross asymptotes. There can be an asymptote in a graph, like I've drawn here, but the graph also have a point on the graph. How about a horizontal asymptote? Let's use this limit, these limit vocabulary words.
So a horizontal asymptote, well, that's when we're having like our end behaviors going towards something but not reaching it. So that would be like, what's the end of the numbers? That's infinity, right? Or the end in the other direction is negative infinity. So we would probably say f has a horizontal asymptote at y equals k if and only if the limit as x approaches positive or negative infinity of f of x is some number k. Oh, you use the plus or minus there. I see.
I did. Is k. Like in my example here, actually, let me do this. Just so I don't have k is equal to 0. That's kind of boring. A k here is like y equals k. It's a positive number, it looks like. As my x value goes off to infinity, my f of x value is getting closer and closer and closer, arbitrarily close, as close as you want, to k. That's the big idea, is that it's not just, it's getting closer and closer and closer. And if you say, when's it going to be 0.01 units away? I can give you a number where it's that close. When is it going to be 0.000001 units away? There will be a number eventually. That's the idea with horizontal asymptotes. And I said something a second ago that I want to like reiterate. Graphs can cross asymptotes. Here's like one of my favorite examples. I don't remember the function rule. If you remember, Mrs. Contreras, let me know. But like, this is getting closer and closer and closer and closer and closer, arbitrarily close. If you want to be super duper, if you want to be 0.0001 away, eventually you'll be that close. I have a horizontal asymptote here, and I'm constantly crossing it. This is an interesting example of an asymptote. It's a common misconception that you have to like be approaching it from one side. I think that was clear.
It's like a sine over.
It's probably going to look like sine over x, but it's not sine over x because crazy stuff happens at the origin. All right, let's not get into sine because we haven't done that yet in this class. All right, let's look at some asymptotes. Let's get these graphed.
Graphing, we know how to graph that. That's just
Oh,
a function. So 1, 1, negative 1, negative 1.
Negative 1/10, or negative 1/10, negative 10.
And then our domain is negative infinity to 0 and 0 to infinity, not including 0. Our range is the same.
I'm going to write it a different way.
Wow, getting crazy.
Yeah, getting crazy. All right, increasing intervals.
So it looks like we have only decreasing intervals.
It like kind of looks like it's increasing, but it's totally not ever. I think this one's like deceptive. This is NA, not increasing. But you said it's always decreasing?
For its entire domain.
Yeah, so a lot of ways we can write this. I'm just going to write negative infinity to 0 and 0 to infinity. But we could say like always on its domain, things like that. All right. Is there a value? Is there an equation of a line? Is there a line that this graph is getting arbitrarily close to as so this is asking for asymptotes in general, so both horizontal and vertical. Let's tackle vertical first. Is there a value that this graph is going towards where it's getting it's becoming infinity or negative infinity?
Yes, at x equals 0 is a vertical line.
As the graph approaches 0, its function value goes to negative infinity and positive infinity, depending on the side that you're approaching from. And do we have a horizontal asymptote? As I go out to infinity, am I getting arbitrary close to some value, some y value?
I think so. I think it's y equals 0.
Y equals 0. Right. And how far do I need to go out to be within 1/100th? This is the 1 over x graph. Think about it. I want to be 1/100th units away from the horizontal asymptote. How far do I need to go out?
100?
Close. You will be exactly 0.01. You will be 1/100th away. How far do I need to go out so that I am closer than 1/100th?
More than 100?
101. 100.01. Cool. So there exists a number that I can get as close as I want. That's kind of the idea. All right, negative 2x plus 3. I'm not just this one's not a parent function. Help me out.
So we have a parent function 2 to the x. Maybe we can think through the transformations. And then it's negative 2 to the x, so that's going to be a reflection across the x-axis. And then we're going to do a vertical translation 3.
So I think that puts the asymptote at y equals 3.
Mm-hmm.
I've just given away one of the answers. Darn it. So you flipped, we went up 3. I call this the happy point. For all exponential graphs, it goes through 0, 1. So it's the happy point. It's just you're happy. You get it for free. So I believe it's going to look like this. And I'm going to kind of fail on graphing the rest of it. Maybe I should be a little more detailed. Let's see. I'm kind of thinking about this as if it was a regular 2 to the x graph. Like and this is my origin, and this is my positive x-axis. So I have 0, 1. Then if I go over 1, I'm going to be at 2. If I go over 2, I'm going to go down 8.
I think, Mr. Kirk, you did like 2 reflections.
Am I doing the wrong thing entirely?
I think so.
Uh-oh.
Because I think you reflected, so you took your parent function 2 to the x, and then you did negative 2 to the negative x.
Ah, you're totally right. All right, but I need to fix a few things, right?
But you can keep your happy point.
I can keep my happy point. That's true. All right, so over 2, down 1, 2, 3, 4, 5, 6, 7, 8. And there we go. All right, just like some of my tricks, and I totally messed up I did an extra reflection, as you said. But there, I just missed all of those points. That was it. But
you can move it. You can like select it and then shift it.
No way. No way. It's moving one of the points, but whatever. That's cool. Kami is pretty powerful. Law of large points. I'll fix that one just by making the point larger.
Is that a thing? Law of large points? You've said that
several times now. It's something I do. It's totally not a real thing. Let's leave these for the viewer. Think about those. Domain, range, increasing, decreasing, asymptotes, extrema. All right.
Maybe a monster of a question.
Discontinuity. All right. So we got some more definitions for you. There are 3 types of discontinuity. To talk about them, I think I want to graph the picture first, then give it a name, and then talk about its definition. Is that cool with you?
That sounds good, because we're really used to graphing now.
Yeah. Like, because I'm looking at these, I'm like, parent functions, let's transform them. we're going to the, what is that? To the positive right direction, 3, and then down 6 for a parabola?
Yep.
3,
So our
4.
vertex is at what? 3, -6? Yeah.
Yeah, I think, and that's something that many people deal with in geometry is the vertex form of a parabola. So that might even be a recap. All right, so we got that vertex, and then it's just a regular parabola. So once again, it's like riding a bike. And it looks like I'm just graphing this parabola 1, 2, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. But the problem is there's no point there. It's really at 7. That's what the second part here is saying. If I go over 4, I should be going up 16. So 9, 10, 11, 12, 13, 14, 15, 16. Perfect. And I have a little bit of symmetry. Take advantage of that. Awesome. Let me try to graph this. There's a hole there. Piecewise function, complete. Sweet. All right, so can you kind of like put discontinuity into like layman's terms?
It's when your graph doesn't have all of the x values that you want, where you
think they're going to be.
How late are we going?
My thought is, if I'm graphing it, do I have to pick up my pencil to then continue?
Oh, that late. Okay.
that late. Yeah.
Yeah. If you're using a physical pencil, then you're not picking up your physical pencil while you are drawing your graph.
Right, but like, yeah, but what you were saying, I like that too. Like when you're graphing something and you think it's going somewhere, and then it doesn't. It goes somewhere else, which is happening here, right? I'm going up. When I get to this point, like if I was not given this piece of information and I wasn't given the left side of this graph, I would probably predict that it's going to go to 0, 3. But we've been told in this problem that actually at 0, the graph is 7. Right? This is called removable discontinuity. Can you give us the actual definition?
So we have a removable discontinuity if going back to our idea of limits, the motion that we have as we're approaching all of our, or that one particular x value, so that input, which we're saying right now is 0, but we could call it a.
So I'm going to say f of x has removable discontinuity at x equals a if
the limit as x approaches a of f of x does not equal f of a.
The limit as x approaches a of the function does not equal f of a. Right, so here, f of a is, our a is 0. We're saying that there is a removable discontinuity at x equal, I'll do the new color, x equals 0 is removable because at f of 0, we have 7, but the limit as x approaches 0 of the function, right? What is the graph approaching? It's approaching 3. Right? 7 does not equal 3. We have a removable discontinuity here. We're approaching something, but when we get to that thing, it is not that thing. That is what removable discontinuity is. Cool. Okay,
There's the layman's way of thinking about it too, right?
What is that?
Well, it's like if there's a hole, then you can just fill in the hole and make it continuous, and you're good to go.
Yeah. If and another way to think about it is if you just put a point there, does it become continuous? Can you then graph it without picking up your pencil? All right, here's a graph that's a little bit more obnoxious to graph. H of x, absolute value of x over x, Any ideas on how to graph this one? This doesn't look like one of our parent functions.
It looks like it's going to be horizontal lines, but not in like a nice way. So if you plug in any positive number, then you don't have any sign changes for the numerator. So it's a positive over itself.
Which is like 1, right? Like, yeah, 5 over 5 is 1, 1 over 1 is 1, 2 over 2. It's the horizontal line. X over x is basically 1.
But then when you have 0, that's going to give you a undefined, because you're having something divided by 0, so you get a whole.
Mm-hmm.
And then if you plug in any negative number, like, I don't know, -7. Absolute value -7 is +7. Divided by -7, it's -1. And the same goes for any x's that are negative. Your value is going to be -1. But again, we can't include 0 because 0 still gives us undefined.
All right, there's our graph. Absolute value of x over x. All right, what is this kind of discontinuity called?
It's called a jump discontinuity, because you can just, if you jump from one to the other, you can still get there. It's not impossible.
Right. Imagine you have like a super frog.
What's a super frog?
It's a frog that can jump any real number distance.
Wow.
If you can jump a real number distance, if you can like kind of define the distance between the 2 points that you're jumping from, I think you got a jump discontinuity. It's a little bit a vague hand wavy definition, but a super frog, if you can jump. Can we give this a real definition?
Yeah, but we have to use that like funny like notation that we were using. With
F of x has jump discontinuity if, when you say silly, or not silly, but the notation.
The kind of like, oh, the left.
Left, right. So let's just make this a little bit more clear. F of x. So tell me the definition, and then we'll talk about the definition. So f of x is jump.
The limit as x approaches a from the left of f of x is equal to a number, and the limit as x approaches a from the right is a number, but those two numbers aren't the same.
Is that cool?
That's great.
Sweet. All right, so let's briefly just talk about this weird notation here, minus and plus. Right? While it's minus, it doesn't necessarily, in our example here, it actually works. But that minus doesn't mean negative. It means from the side less than that value a. All right, so if a is 73, 72 is to the left. It is more, it is to the left on the number line. So that's what we mean by this negative, from the left. And then the positive just means from the right. Right, so don't notice that negative is a superscript. It's like an exponent. It's just a symbol, not a number, not to confuse it with exponents. But it's a superscript. It's not in front of the number to confuse anyone about negative a. It's a whole new use of the negative and the positive symbol to mean left and right. Left and right, respectively. Left, right. Right. But you also said something really important that I want to reiterate. They both equal real numbers. That's the idea of my superfrog. Superfrog is, it can jump a real distance, but it's not a deity. It can't jump an infinite distance. Right, so both of these actually equal a number, but they're not the same. So what am I approaching from the left-hand side?
We're approaching -1.
Okay, so in our example, the limit as x approaches 0 from the left-hand side of our function, and I shouldn't say f, I should say h, because that is what it is -1. That's the number we're approaching. The limit of h of x as x approaches 0 from the right side is, what is that?
1.
1. Right? They are not the same thing. We have jump discontinuity. Like the distance here is like hand wavy 2. Superfrog can jump it. All right. This is where Superfrog, I've made up this analogy, by the way, right now. This is completely new. Superfrog. So if there's any pitfalls in my analogy, let me know. All right, Superfrog is not a god, though. Superfrog can't jump infinite distances. So we got this last discontinuity here. You do need to pick up your pencil when graphing this. Let's graph it real quick. We got our parent function is
1 over x.
1 over x. We're shifting right 3, up 2. So I got some asymptotes that are moving. Let me change the color. Let's go like dark green for Superfrog. Although frogs aren't always green. Kermit the Frog is though. And that's the most important frog. That's not a debate.
Now I want to debate that.
No, you can't debate it. It's not allowed. All right, and then we've been dilated by 4, so I know this point that was 0, 1 is now going to be, sorry, that point that was negative 1, 1 is now going to be negative 1, 4. Not negative 1, 4, but it's going to be dilated now. That point that was over 1, up 1 from the center is now going to be over 1, up 4. Same thing down here.
I think you did the reflection thing again.
Did I really? Yeah, I did. Wow, I'm just like not on it with reflections today.
It's okay.
If anyone has any complaints about this, just write about it in your journal. And then I believe the point 1/2 now became 2. So it's going to be right there. And that's good enough for me. The point that was 1/2 away from the asymptote is now 2 away from the asymptote. Okay, there we go. We got our graph. Cool. I'm happy. I'm just thinking out loud about how I graph these things. I think that's useful. All right, we have a discontinuity here. We must pick up our pencil to graph this. You can't see the cursor. I forgot again. We must pick up our pencil. So let's give this a name, and then let's give it a definition.
I think it's an infinite discontinuity because it is an insurmountable distance for Superfrog.
Superfrog cannot jump this distance. Infinite discontinuity.
Not even if someone tosses him.
Discontinuity. Not an annuity, a discontinuity. That was a really stupid joke. Infinite discontinuity. Superfrog cannot jump this distance. All right, Superfrog gets sent down this slide and then must figure out a new way to get up here. Must figure out how to teleport or something, but it cannot jump it. He cannot jump it. What is our definition to this one?
When we have our limit as x approaches a of f of x is positive or negative infinity.
Yeah, this one's kind of easy to write. F of x has infinite discontinuity at x equals a if either the limit of f of x as x approaches a from the right side, sorry, the left side, is plus or minus infinity, or the limit of f of x as x approaches a from the right side is plus or minus infinity. If infinity is involved, Superfrog can't jump it. That is our definition of infinite discontinuity. So we got some limit notation in today. That's kind of cool. That's like a little homage to calculus. Let's keep going. This next page is hopefully a little bit quicker. All right, here we are. Oh my gosh, it's Superfrog.
Whoa.
What? Mary Kate has saved the day. That is amazing. Can Superfrog just be here now? Yeah. Is that okay with you? Superfrog is now in my background.
Wow.
That's wonderful. Everyone give a round of applause to Mary Kate for bringing Superfrog. Coming in clutch. All right, we are back. We are talking about bounded functions. What does it mean to be a bounded function? Well, yeah.
Well, I think it means that there is a value that your function is going to be less than or greater than for whenever you plug in whatever, like for the entire domain or for however much of your domain that you care about. Your function is going to be less than something or greater than something.
I think I've tried to draw a picture with your description. Like I've drawn a graph here, and I'm going to claim that it's bounded. Because you're saying for a graph to be bounded, it needs to be less than, always less than. It must never exceed a specific number. But it must also never get lower than that number. I think it's magnitude away from the axis. Its absolute value from its distance from the axis needs to be less than a number always. I think I can write that out in math notation. All right, a function is bounded. And then since we're writing this off the brain, help me clean this up and make sure that it's something that we are happy with. A function is bounded if there exists a number m. Maybe I could have used a better number like b, but I'm using m. That's whatever. Function is bounded if there exists a number m contained in the real numbers. And it must be a real number for those who are like all up in arms about imaginary numbers, complex numbers. It must be a real number. A function is bounded if there exists a real number such that what's the distance a function is from the x-axis? What do we write when we want that?
Distance from 0 is the absolute value.
So such that the absolute value of the function, right? A function, let me do this, a function f of x is bounded if there exists a value m such that the distance, the absolute value symbol, of the function it is from the x-axis is less than or equal to that number. A function is bounded if the graph's absolute value is always less than a number. So like, let's say that this is like y equals 7, and this is y equals -8. What is a number that this function is bounded by?
8.
8, right?
Mm-hmm.
And actually, let me make this like super clear. Oh, that was sad. The whole thing went away. Right. 8 bounds this. What might be a guess that is wrong?
3. I guess 7.
7, right? Like that was like my you know, that like multiple choice thing where there's one that's going to distract you, my distractor option. If you said 7 was a number that bounds this graph, you'd be wrong because this graph gets down to really close to -8. If you said that the absolute value of this function is always less than or equal to 7, you'd be wrong because when it's like at -7.5, the absolute value is 7.5, which is not less than 7. Right? So we are looking, when we are claiming that a graph is bounded, we are trying to find a number that this is always less than. Is there like an obnoxious number that this is always less than?
5 billion.
5 billion is the number of the day. 5 billion is the number of the day. We should just try to figure out the special properties of 5 billion. It's even. Anyways, it's large. Well, I guess it's large compared to the numbers we usually use, but it's small compared to other numbers. All right, a function is bounded if there exists a number that the graph is always less than, and its absolute value. So it's the negative and the positive are less than this thing. It's magnitude from the x-axis. But that's not the only way we can describe bounded functions. There are 2 other important words that we want to include. Bounded above and bounded below. So let's go ahead and write those down up here in like a new color. Let's go in Kermit the Frog. That's not Kermit the Frog green, but bounded.
Grouch green.
Yeah, bounded above and bounded below. Let's go ahead and write those down. When I say something's bounded above, what do you think I mean?
It means that there's a number that's bigger than all of your function values.
Yeah, no absolute value. Right, so if I got rid of my dotted line here, I'm not going to get rid of the dotted line, but if I get rid of my graph, right, this graph that I've just drawn is bounded above by 7. Right, because we're no longer concerned about the absolute value. When we say bounded, we mean both sides. It is been closed within upon, like in the episode of Star Wars where the trash heap is closing in.
The trash compactor?
Yeah, the trash compactor. What do we mean bounded below?
So more like
it's like a function of y.
Yeah, but I think it's more like in like the droid factory when there's like the crushy thing.
Yeah, you're bounded. You get the floor and you got the crushing thing.
Mm-hmm.
How about bounded below?
Bounded below is that there's a number such that the function is always greater than or equal to that number.
There exists a number such that the function is greater than or equal to that number. We are bounded below by the Earth if we're talking about our distance from the Earth, right? The center of the Earth.
Okay.
We can dig a hole. All right, there we go. So when we say, hey, is it bounded? Which we will do, we mean that it's bounded above and below. And then if we mean to only say one of them, we will then clarify. All right, but bounded is referring to both sides. Are we bounded physically below by anything? Only with a closed mindset.
I'm bounded by my feet and the top of my head.
When you're bounded by the feet and top of your head, are you bounded above by anything is what I meant to say.
When I'm inside, I'm bounded above by the ceiling.
I think you're just not destructive enough.
Okay.
All right, let's proceed. All right, periodic functions. This definition is real simple. I think I'm just gonna write it down.
Sounds good.
A function is periodic. A function is function f of x is periodic if there exists a value p contained in the real numbers such that f of x is equal to f of x plus p for all x contained in the real numbers. All right, let's construct a periodic function.
Okay.
And I think that make this this definition a little bit more clear. P is a real number. Let's go ahead and say P is like, pick a number, a reasonable number. Don't pick 5 billion.
3.
3. Okay, so let P be equal to 3. Okay. We're constructing a function. Give me a point for this graph. We need to start somewhere.
0, 1.
0, 1. I'm gonna do this in a new color. 0, 1. All right. What must be true because of our definition?
We should also have the points 3, 1, and 6, 1, and 9, 1, and -3, 1.
Let me get some more of these just in a second, because I have a feeling they're going to be important. But you said f of 0 is equal to 1. So f of 0 plus 3 must also be equal to 1. But then you started to like cascade. You're like, okay, well, 3 is equal to 1, so 6 must be equal to 1. F of 6 must be equal to 1. 6 is not equal to 1. That's not true. 9 must be 1. I did it again. F of 9 must be 1. F of 12 must be 1. You went the opposite direction. You said, okay. A periodic function is where this is always true, though. What we've drawn here, if we were to continue drawing it, would be a periodic function. It's quite boring. Let's give ourselves some more points.
I want to do the teeth function that you had, the zigzag one. So
okay.
let's see. What do we need for that? Like 1, 2.
1 comma 2. So you're saying f of 1 is equal to 2. So what must be true?
That f of 4 equals 2 and f of 7. No, yes. 10, 2. Mm-hmm.
I think I got 13 2 as well. How about f of negative 2? Is that also 2?
F of negative 2 is also 2.
Okay.
And then let's see, f of 2, let's get a 0.
F of 2 is 0.
Mm-hmm.
So using your definition, f of 5 is 0, f of 8 is 0, f of 11 is 0, f of 14 is a 0, f of 1 is 0. Okay.
Negative 1. Let's just connect all those with little line segments.
So you want to do with line segments? Boom, 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 boom.
It's not exactly your teeth function.
Yeah, and clearly my scale, if you notice, I did a very bad job approximating these grid lines. It like slowly gets bigger and bigger and bigger. That's supposed to be the case. Right, that point right there is also going to be 0. All right, but I believe this is periodic because no matter what point, we just filled in an infinite amount of points. But no matter what point, if I go 3 away, I will be at the same output value. Pick a number that we didn't previously plot that's on this graph now, and we'll verify if this is periodic.
1/2.
1/2 outputs something. Based on the graph, it looks like it's outputting 1, comma 1.5.
Yeah, sounds
no,
good.
sorry, 0.5, comma 1.5. All right, so when I add 3, 3.5 should output 1.5 as well. 1, 2, 3.5.
Hey, that's pretty good.
Yeah, not too bad, not too bad. This is a periodic function. We have lots of periodic functions, but in order to verify whether a function is periodic, this equation must always be true for no matter what x value you pick. And there are lots of good classic examples, but we haven't gotten to those yet. So here is a made-up one. But some of you may be thinking about certain graphs that you maybe studied on your own or maybe you've seen before that are, in fact, periodic. Cool. All right, I got one last problem for you, Mrs. Contreras, and this is something that I referenced at the beginning of the lesson. All right, so we are now at the point where, given a list of properties, hopefully we can construct a function that meets these properties, that meets meets our definitions.
I see a list of properties. I feel like we're gonna need to sketch a function.
All right, so f is even. We know what that means. That means when you plug in a number, when you plug in the opposite of that number, you get the same thing.
Or it's symmetric with respect to the y-axis.
It's increasing from -infinity to -3. Its domain is all real numbers. That's just a lazy way of writing. The domain is all real numbers. The domain is equal to all real numbers. It's continuous, so we're not going to have any discontinuities. F has a horizontal asymptote at y equals 5, and f of 0 is equal to -2 is a relative min. Okay. This is no easy task. What do you want to do first?
I want to plot the point 0, -2.
Boom. OE in purple. Okay. I think that's a good idea. Put the things down that are like set in stone and we don't have any choice. I think y equals 5 being an asymptote is also something maybe we should sketch. That's a pretty badly drawn dotted line, but we'll live with it. Okay. It's even. It's increasing from -infinity to -3. All right, but wait, that's an asymptote. And it's even. So like what must be happening as I'm going off to infinity?
we need to get closer to y equals 5.
Right. So I recommend doing these.
It's also even, so we know that as we're going to positive infinity, we need to be getting closer to y equals 5.
So I recommend doing these problems in pencils, because is there a problem if I approach the asymptote on the right-hand side from the bottom? Because you said it's even, so now it's going to pop up over here, right? Do I have a problem?
But then it's not increasing from negative infinity to -3.
So it's an asymptote. So as we go off to infinity, we need to be getting closer. But I can't be approaching from the bottom, because if I'm approaching from the bottom, then I'm going to be decreasing. So I need to be approaching from the top. And I need to be increasing. So I'm increasing, and I believe I'm increasing until -3. So let's just like increase until -3. And if I choose that, then I need to do the same thing over here.
Because it's even.
Because it's even, yeah. All right, so let's check what we got. We are currently even. So I'm gonna go ahead and check that. We're making sure we're even. We're currently increasing from negative infinity to 3. We have our asymptote at y equals 5. F of 0. We have f of 0, but we haven't made it a relative min yet. So we need to address the fact that this is the lowest it gets. It's a relative min, so it can get lower, but on an interval around that point, it needs to be the lowest. But we need to address these two things. Domain is all real numbers. It's continuous on R.
Could we just do like an absolute value function? Absolute value function that connects from negative, when x equals -3 to...
Kind of like this? Am I graphing what you're saying?
Yeah. It's like the Tesla logo, kind of.
Oh, yeah.
More like the, what's that? The one, the Texas Longhorns?
The Texas Longhorns? I feel like they do so. I don't know. Yeah. Wait, did we just... All right, so let's double check that we're meeting everything. It's even. It's increasing from negative infinity to -3. Its domain is all real numbers. It's continuous. Yep, no holes, no removable discontinuity, no jump discontinuity.
Super Frog can just walk on over.
Yeah, no hopping necessary. It's continuous. We just said that. We have our horizontal asymptote. And f of 0 equals -2 is relative minimum. We're done. Boom. Well, I got an issue. I crossed an asymptote. How is that an asymptote?
Because we're looking at the end behavior for asymptotes. But I do have a concern.
Okay.
That it specifies that f of 0 equals -2 is a relative minimum, not an absolute or a global minimum.
Okay.
So should we make sure that we are demonstrating our understanding of a relative minimum by showing that it's not the absolute minimum?
Oh, so you want to go, I think, above and beyond, because is that not a relative min and an absolute min at the same time?
Oh, because there exists an open interval such that -2, f of 0 equals -2 is less than or equal to all of the x values in that interval.
Yes. Can we do what you're saying, though, go above and beyond and make it only a relative min? It doesn't say only, so we were correct before, I think. But can we go above and beyond?
I think if we do something like a W.
Boom, 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 boom. It's like an M and a W.
M and, yeah, it does, yeah.
It's
not very even.
I know.
Oh, no.
Like, let me do that. Let me do that.
There you go.
Let me do that, and then let me whoop, whoop. What does that look like?
I don't know. It looks kind of like a I don't know.
Only a relative min, right? It doesn't ask for that, but we can go above and beyond to make sure that is understood. I don't know what it looks like. It looks like something that's in Adventure Time. You know that show? That's what my mind goes to. It's like when you look at the clouds and you're lying on the grass and you're looking at the clouds. You're like, that looks like a thing. It's what you see.
Mm-hmm.
All right. We have sketched a function that met a bunch of properties and required a decent understanding of each of these properties. I'm going to scroll down. We're not going to do this next one, but we do implore you to try to do this one. F is bounded on R, it's continuous on R. It has a domain of R, and it's always decreasing. Try to do this one. This is going to be left to the viewer. But I think with that, this is a long video. Let's go ahead and close this one out. Got an icebreaker?
Icebreaker. What's the last thing that you ordered on the internet?
What's the last thing I ordered on the internet? Let's find out with my Amazon app. I think yesterday was like Amazon Day or something like that.
Oh, Prime Day.
Prime Day. Did you buy anything?
No,
Neither did I.
because we forgot that it was like Prime Day, and also we already have an Instant Pot, so like, what else do you really need?
Oh, the last thing I bought was Super Smash Bros. Ultimate.
Is that a game?
It's a video game, yeah.
Okay.
For my Nintendo Switch, yeah. So any Super Smash Bros. People out there, that one's for you. But yeah, that's the last thing I bought. And what did you say you bought? You said you bought an Instant Pot last?
No, we had an Instant Pot for a while. Instant Pots are amazing. Highly recommend. We're not sponsored by Instant Pot. We just really love them. But
I'm sponsored by Nintendo.
We've just been buying coffee. That's pretty much the only thing that we've been buying recently.
Yeah. All right, ready?
I did it too fast.
I think it was highlighted on me. So
it doesn't matter.
Yeah.